Okay, so in this second talk, I'm going to say something about Muon relaxation functions. I'd like to thank Francis Pratt, who gave me a couple of the later slides, although I might have to skip those because of time. It's moving along a bit. So, of course, what we're going to be doing a lot with we're thinking about relaxation functions is we need to bring in computers, and so you'll see later on a number of data analysis sessions. So this is a shot from Winder, which is a very popular program developed by Francis, used here. So here you can see some data being fit. Of course, other packages are available. You'll hear about one from Roberto later on today. So there are a number of ways of fitting your data. So what am I going to say in this lecture? I will first of all start to get technical a little bit and talk about some particular distributions. I'll talk about some dynamic relaxation functions. I'll say something about stretched exponentials, say something about quantum effects, and also a little bit about the Muon site. You'll hear more about some of these things later. Again, you're going to get the notes from this, so I will go quite fast in some places. In some cases, what I've done is I've given you quite a lot of maths on the slide. I'm not going to go through all of that now, but I will try and just describe the principles so that if you're interested, you can work through later. So let's first of all think about a muon in a static magnetic field. So this is kind of quite a fundamental experiment. If you have a muon spin in this direction and you have a magnetic field oriented at an angle theta, then you can measure the polarization in the z direction, and simple calculation will give you the basic law of spin precession, which is that part of your polarization is preserved, the cos squared theta part, and the sine squared theta part multiplies an oscillating function. So here, the B here, the modulus of B is the modulus of the local dipolar field. So as you remember, I was telling you about how an arrangement of spins will give you a local dipolar field. This is how you then measure it. Okay, I'm afraid quite a few of these slides are handwritten, so hopefully you can read my writing. So this is what this formula looks like. If theta is 0, so the magnetic field and the spin are parallel, then the polarization will just be preserved forever and ever. On the other hand, if the magnetic field is at 90 degrees to theta, you will see an oscillation that goes all the way between full polarization and negative polarization, where the muon will do complete precession. So, as you can see, the polarization that you get depends very much on this angle. Now, something you can ask yourself is, what happens if we average over all angles? Let's imagine that we've got magnetic fields of a constant magnitude that have different angles all the way through your sample. So what you can do is you can do angular averages. These are averages taken over a sphere. And the average of cos squared theta is a third, the average of sine squared theta is 2/3. So if you had a situation where the magnitude of the magnetic field was constant, but the angle was uniformly distributed in all directions, what you would get is now cos squared theta becomes 1/3, sine squared theta becomes 2/3, and you'd have this kind of precession going between full polarization and -1/3. And this is known as a polycrystalline average because this is imagining that you've got maybe a polycrystalline sample, lots of little grains pointing in lots of different directions, and they are then giving you this average. Okay, now the next thing you could do is say to yourself, let's imagine that the x, y, and z components of the magnetic field are not constant, but they have some distribution. And the helpful thing we can use here, which often turns out to be correct, is that when you take lots of complicated distributions and you convolute them together, you have this thing called the central limit theorem, which basically says with enough complexity, everything is Gaussian. Okay? However complicated those individual functions are, if you convolute them enough times, you'll get a Gaussian. And that works for lots of statistical processes. This is an approximation. We'll think later on when it might not work. But for the moment, let's just imagine this is the case. So let's imagine that we've got some distribution of magnetic fields in our sample. due to some maybe random electronic moments, or more likely random nuclear moments. Nuclear moments are very weakly coupled with each other, and so they are very likely to be pointing in lots of different random directions. Then the central limit theorem might tell us that the probability of finding a magnetic field in the sample in a particular direction, let's say the x direction, will follow this kind of Gaussian behavior with some width, which is called delta. Now, if you remember the kinetic theory of gases, where you have the similar physics, the x velocity or the y velocity or the z velocity of a molecule bouncing around in this room follows this Gaussian distribution. But what you're really interested in is not the components of the velocity, but actually the mean squared speed. And so when you work that out, you get this thing called the Maxwell-Boltzmann distribution. And that's, again, what you would have with the probability of the total magnetic field. The x, the y, and the z components added together in quadrature. Okay, so now what you can do is you can go back to that earlier result that we had, where we had the, let me just wind back and show you, where we had the magnetic field going between 1 and a minus a third. This is where you remember we have all possible angles, but we have the magnetic field fixed. Now we're going to have the magnetic field according to these distributions, and so what we would expect is we get lots of these things adding up together, and you can see roughly what's going to happen is, to begin with, they'll fall off. But over here, they're all going to interfere, and we'll get something which is at the average, which is at 1/3. So what you might expect is that you would get something that drops, and then maybe flattens off to a value of 1/3. And so let's see if that's correct. You can do the calculation, you can do the average. I think I haven't given you the working for this, but I've given you the integrals if you want to derive it analytically. And so I've done the hard bit for you here. Again, as I said, you can look through these notes again later. And what you will find is you get this particular function. This is the zero field Kubo-Toyabe function. This was worked out by Kubo, the great Japanese theoretical physicist, and his PhD student back in the 1960s, not for MUSR, but for a problem they were doing in NMR, where they were trying to look at zero field NMR. And I think a lot of the NMR people at the time might have thought, typical theorists, they're working on a problem that you just can't use. So this got published in some rather obscure conference proceedings. And a number of years later, it was realized that this was important for MUSR, and in fact Kubo was on that later paper in the late 70s. Anyway, this is their function, the Kubo-Toyabe relaxation function, which you just get by plotting out that function. So now what we've done is we've averaged over all angles, and we've averaged over all components of the magnetic field, assuming Gaussian distributions. And so the key features of this curve, it falls away roughly Gaussian. It has a minimum at a value which is roughly 1 over delta. It's actually root 3 over delta. And then you get this 1/3 tail, which, if you remember, you can think about as just being the average of all of these curves interfering and giving you the 1/3 tail. Okay, now the next thing that you could do, if you want to make things even more complicated, is you could apply a magnetic field yourself in the experiment along the muon polarization direction, along the z direction. And what basically will happen in that case is you will get an increase of this 1/3 tail. And essentially what's happening here is that the muon is becoming more strongly coupled to the applied magnetic field than it is to its neighbouring environment. And so this kind of curve can be fitted. The expression is not terribly pretty. I mean, this again shows you how you can think about it. So with no longitudinal field, you see this range of internal fields which are Gaussian in distribution. 1/3 of them you can think of being parallel or anti-parallel to the muon spin. 2/3 of them are perpendicular. If you now add a longitudinal component, what you're doing is you're taking this distribution and you're moving it to the right. So the net magnetic fields are now all these green arrows. And if you like, you can think of this cos squared theta, which was 1/3, is being boosted. And these oscillations, these rings, are going to be slowly suppressed. And that's, of course, exactly what you see. The 1/3 tail goes up, and you see some oscillating terms that get faster and faster, which are approximately ringing, oscillating at this longitudinal field. If you want the maths for this, you have to integrate with these probability distributions. Now with an offset, you have to evaluate this integral, and this is much more of an algebraic pain in the backside, I'm afraid. So you end up with a bit that actually you still have to represent as an integral. Fortunately, all of these functions are coded in your favourite fitting programs, and so therefore you don't have to worry about these precise expressions. Now, as I said, we've been assuming that the magnetic field is distributed according to a Gaussian distribution, and that is somehow justified by this thing called the central limit theorem, which basically says if you get a whole lot of complicated distributions and you convolute them together, you get something that approaches a Gaussian. And so you could imagine that the muon sitting in a particular environment, it's maybe seeing the effect of neighbouring spins. Each one of those neighbouring spins gives you a particular distribution that might be quite complicated. But because you've got a number of neighbouring spins and you're coupled to all of them, maybe they convolute together and you get something that is Gaussian. So this is a reasonable approximation. And for your data set, you can try it and see how well it works. However, in the case of dilute spins, it turns out that you can show that the distribution should be approximately Lorentzian. And in that case, you can go through the same algebra that I've done before, and you can derive these expressions for zero field and longitudinal field in the case of a Lorentzian distribution. Lorentzian is basically a function which is just something over a constant plus, and then your field squared. And it looks rather similar, except it's got tails that decay away more slowly than a Gaussian. Now, unfortunately, the expression that you get in longitudinal field does look a little bit like an explosion in a mathematics factory. So you end up having things like spherical Bessel functions in the final expressions. But the way they look is much the same. I've actually sketched these, but they look very similar to the traditional Kubo-Toyabe ones, but their form is slightly different. Fortunately, again, these will be coded in your basic, coded into your analysis software. Now, when are dilute spins important? Well, having a broad range of couplings from the muon to the nearest spin is the key here. So, in this particular case, a metallic random alloy spin glass, you've maybe got a number of magnetic sites, and some of the muon sites are quite close to a magnetic site. Some of them, like this one over here, is a long way away from a magnetic site. Another possibility that you could have, which is indicated schematically here, is you can have a magnetic spin quite dilute, because you're maybe dealing with a complicated molecular magnet, and the muon sites, maybe the muons go all over the place, which is schematically illustrated here by filling the space with stars, although probably they'd be more randomly distributed, or apparently randomly distributed. So you may have a distribution of couplings between spins and your probe, just because there are loads and loads of different sites in a very complicated material. And so this could be important for giving you a kind of Lorentzian distribution. Again, all of these functions are available in WIMDA or indeed in your other package that you happen to be using. Now, something else that we can do is we can introduce dynamics. Everything I've said so far assumes that your probe spins, that your muon site and indeed your local environment is static. So they produce a constant magnetic field, which is just like this for any individual muon. But what happens if there's dynamics? This could be of two origins, mainly. One could be that your muon hops from site to site every now and again. And every time it hops, it sees a new environment. So it starts processing, and then it hops and sees a different magnetic field. So it starts processing in a different direction, and then it hops again and sees a different environment. So that could be one source of dynamics. Another source could be that the muon stays completely stationary, but its environmental spins are fluctuating. So these are all possibilities. Now, it turns out one can then interpolate between statics and dynamics using dynamical Kubo-Toyabe functions. So, for example, if your muon spin is, if your muon is static, there's no dynamics, and let's imagine the environment is just like we've been describing with a Gaussian distribution of local fields. Now we start allowing the muon to hop, or the environment to fluctuate. In the limit of very strong dynamics, the muon doesn't really care about this Gaussian distribution. It will start to show this exponential relaxation. And the dynamical Kubo-Toyabe function will allow us to interpolate between the two. Now, how does this work? How do you derive this? Now, I'll go through the traditional derivation of this. Roberto, sitting at the back, has got some nice new ways of working these things out, but I'll just give you the traditional approach. This is the so-called strong collision approximation. Basically, what we're going to assume here is that the local field on the muon is suddenly changed by what's called a collision. Now, this collision is just some event where everything changes dramatically. This terminology comes from a different field, but the collision here we should maybe just think about as the muon hopping and essentially resetting its environment. So its environment now becomes completely different. And so what we're going to assume is that, so this is an assumption, is that the environment is randomly distributed with no correlation with the field before the collision. So this is known as a Markov process. So we're throwing the die and getting completely new random numbers giving us the local distribution. And we'll assume that this takes place at a rate which has an average value of nu, and this means that the correlation function of the local magnetic field, so you work this out by working out the average value of the magnetic field at time t and the magnetic field at time 0, this correlation decays exponentially. So what you have to do, and again I'm going to go through this very fast, but I want you just to get the principle of it, the relaxation function that we measure has to be a sum of muons that never collide, muons that do one of these hopping processes, muons that do two of these hopping processes, muons that do three of them, etc. We have to sum them all up. And so, if you like, we're having to sum up lots of relaxation functions for the fraction of muons that do n collisions, where n goes from 0 to infinity. So if they do no collisions, no jumps, then this tells you the fraction of them that have not hopped up to time t. This is just given by this exponential. And then this thing is the static relaxation function. So this is our Kubo-Toyabe, let's say. And then we have to sum up the case of doing one jump at time t1. So what you now have is a jumping probability between time t1 and time t1 plus dt1. Then you've got the equivalent term as we had last time before the jump. So we are showing this relaxation up to time t1, and then this factor gives us what happens after a jump. And then we can derive a similar expression for two jumps. And as you can see, these expressions get more and more complicated because this one is an integral, this one is two integrals. For n, it's n integrals. So this starts to look very complicated. So you end up summing this up. We've got this sum of all of these individual things and the sum of the whole series of integrals. So one way you can solve this, and this is the traditional way of doing it, is you can find analytical solutions by doing a thing called a Laplace transform. And the thing about Laplace transforms is you recognize that these things up here, these multiple integrals, can be represented as convolutions. So even though this thing has got n integrals in, when you take the Laplace transform, it ends up being a product of n things. So you can then end up with this Laplace transform of this just being a power series. And the power series you can sum. So you can work this out, and then you have to just take the inverse Laplace transform at the end. Now the problem with that is the inverse Laplace transform is a real pig. And so that's not possible to do in many cases. So, but at least this is a way of deriving an analytical solution. Now, there are lots of other ways of solving this particular problem. You may hear more about some of this in later talks. The good news is that you don't have to do this. This, again, is coded up in many of your analysis software programs. So this is what it looks like, interpolating all the way from no dynamics to faster and faster dynamics. In fact, there are easier ways to do this. And in fact, because this integral only depends on its value at earlier times, there is a way of sequentially building it up in stages. And so some of the routines do that. Some of them also use lookup tables where some of these functions are stored and interpolated. But what you will notice is when you try and fit with these methods, they tend to be quite slow. So you'll probably notice your analysis software slowing up when you select Dynamical Kubo-Toyabe, and maybe just this explanation has showed you why. It's not quite so simple as fitting with a simple function. Now, in fact, one of the interesting things about this is that the main effect that you get is in the tails. So the first thing that happens is you start messing up this 1/3 tail. So the 1/3 tail, you can see for very slow dynamics, it looks very similar to a Kubo-Toyabe, but actually the first thing that gets hit is the tails. And these relaxation functions, in the tails, the 1/3 tail gets reduced, you can show, by this factor. So the faster the dynamics, the quicker this tail gets hit. On the other hand, if you go to very fast fluctuations, as this tail goes down, but then these curves start coming back up again for faster relaxation and becoming flatter and flatter. And in fact, what you find for the limits of very fast dynamics, when nu is much, much bigger than delta, these things just become exponentials. So they go to exponentials, but the relaxation rate goes 1 over the fluctuation rate. And this looks the wrong way round. Faster fluctuations, and yet the relaxation becomes slower. And that doesn't look the right way round. But the way to think about this is, actually this is something that has been known for many years in NMR. It's the effect that's known as motional narrowing. When you have fast dynamics in NMR, an NMR line becomes more and more narrow. And the thing to realize is that in MuSR we're working in the time domain. That means that as the dynamics get faster and the line narrows in frequency, the relaxation widens in time. So for faster dynamics, you see a relaxation that falls off more slowly. So this is very counterintuitive, but it's worth thinking about. Okay, now something else you can also do is you can try adding longitudinal fields as well as dynamics. I've just plotted some curves there. A rather nice way of analysing some of these expressions is using a function that came from Amit Keren that he derived in the 90s. I'm not going to go through the details of this. I'll leave these in the notes if you want to read through them. Now I want to come to the stretched exponential. Now the thing about the stretched exponential, which you will find on your drop-down window of different fitting functions, this is a very simple function, e to the minus lambda t raised to some power beta. Now the reason I've got this image here is that the stretched exponential is a bit of a danger to you, much like if you took a shower in the Bates Motel. Okay, so the reason it's a danger to you is that it will probably fit your data, and you have to think to yourself, yeah, but does that mean anything? So the problem is stretched exponentials kind of fit almost everything. I should really put an almost there. Why they're so good in a way is that they will interpolate between a number of cases. So a Gaussian relaxation, which is what Kubo-Toyabe start as, would have beta equals 2. A Lorentzian relaxation will give you beta equals 1. And many of the stretch cases are beta less than 1, although I probably should put beta. Beta could be anything. Now, stretch exponentials generally arise from a distribution of relaxation times and a distribution of couplings. But I think it's far better if you can understand what those distributions are and use a more carefully designed parameter. They're a good thing to try on your data and see if it works, because they can sometimes give you some insight when you're still trying to figure out a problem. But try and work beyond that. Although it's often said that they fit a distribution of relaxation time, the one thing I want to point out is that if you try and invert it and say, okay, if we have exponential relaxation with some distribution, what kind of distribution would you need to fit a stretched exponential? This is the answer, this complete mess. Now in some very simple cases, this reduces to something nice, but for most values of beta, it stays like this. And so really you have to say, how can you justify that physically? And the answer is you generally can't. So just because it fits your data, you have to think very carefully about whether or not it's really correct. If you get a distribution of relaxation times due to diffusion, a rather beautiful idea which came from Klaus Kerr is this so-called Risch-Kerr function. And this has been used very successfully to fit the relaxation function in polymers. And this is an approach that Francis Pratt pioneered. And the basic idea is that in a polymer, you can inject a spin defect that can diffuse up and down a chain. It can also move onto a different chain. And this rather complicated relaxation function that contains both a complementary error function and an exponential gives you something that, as you can see here, looks like a Spectra exponential with beta equals 0.4 for these particular parameters. So you might say, oh, this is a Spectra exponential, but in fact, by using the correct physics that more carefully models the experimental solution, gives you much, much more insight. Now, of course, this another thing to think about is that a magnetic field-dependent relaxation also tells you something about the spectral density of the fluctuations. And so a large, if you have a correlation function which is exponential, then you would get a spectral density which is Lorentzian. But sometimes you have much more complicated relaxation processes, particularly those based on diffusion, give you power laws for these things. And so there's a lot more thinking that you can do if your problem has particular forms of the spectral density. And here are a few examples in single molecule magnets and polyaniline. I won't go through these individual examples. Now, something that's also been very important historically in MUSR has been this distribution of couplings. And one of the places you can see that is in the spin glass. So spin glasses were very popular in the 1970s. In a classical spin glass, what you have is something like, let's say, gold or copper, a non-magnetic metal shown schematically here. And then you substitute a few of the gold atoms by iron atoms. Now, in a spin glass, these things are, in this particular spin glass, it's metallic, and therefore this material is completely non-magnetic apart from these little magnetic impurities. And because it's metallic, the coupling between these two iron atoms is a so-called RKKY coupling. This means that the coupling could be antiferromagnetic or ferromagnetic depending on the distance between these two magnetic moments, which is essentially random because these iron atoms go in randomly. So you have a network of magnetic centers that have got random couplings between them. Now the thing is, the muon, if it sits here, it sits quite close to this iron atom, so it will see quite a wide distribution of local fields. Whereas this muon over here is a long, long way away from those two iron atoms, and so therefore it sees a narrow distribution of magnetic fields. And it turns out in that particular case, you get what's known as root exponential relaxation. Now this, of course, is a special case of the Spectra exponential, but it actually has a justification. And so again, just to show you the point, if you have a non-magnetic host, and now we put magnetic ions in, so the magnetic ions are red, this muon sees a very large magnetic field or a very large distribution of fields. This muon is now well away from the magnetic ions, so it sees a very narrow distribution, and that's what gives rise to this range of couplings that you see in experiment. And this range of coupling strengths, if that range of coupling strengths has this kind of distribution, you can show analytically that it will give you a root exponential. Though I must admit I have my doubts as to whether or not this distribution is in fact what you would actually see. So this appears in Yumura's paper, but it's not entirely clear to me where that distribution comes from. That's a number of years ago. I did ask that question and tried to simulate it in a few cases. In fact, what you have, this shows you the filling of a lattice, of a magnetic lattice with different concentrations of magnetic ions, looking at the distribution of those couplings. And what you see is that it looks nothing at all like this. On the other hand, when you can see for very dilute couplings, it's starting to look like that kind of distribution, although there are these other little peaks that appear. Nevertheless, when you try and evaluate the relaxation function, they actually look remarkably like root exponentials for small concentrations of spins. Okay, so I'm giving you a lot of information in this talk, so I know I'm going very fast, but again, you can pick up on some of the detailed bits looking at the notes later that maybe apply to the things that you want to think about. So a few things to remember. The first thing is that the standard fit functions, particularly the stretched exponential, may work. They may fit your data, and again, reminding you of what I said in the first talk, just because theory fits your experiment doesn't mean that it's correct. So it may work, but what does it mean? So I would encourage you, when you do your muon science, to think deeply about what your relaxation functions actually mean. Now, something else is that the fluctuations in magnets are often correlated. They're not Markov. So this is something that you also have to watch out a little bit for when you're dealing with fluctuating magnetic systems. Just don't necessarily use dynamic Kubo-Toyabe functions and assume they're going to be correct. And finally, everything we've talked about so far has assumed that the interaction between the muon and some distribution of fields is a classical interaction with no quantum effects, where the muon might actually also influence the local environment. So in the last few minutes I want to say something about that, about hints of quantum coherence. And this shows you a particular molecular magnet. I won't bore you with what it is. At low temperatures, below the nail temperature, we see some oscillations. And these are to do with magnetic order. So we studied those in some detail, but well above the nail temperature, well above the point at which it's magnetically ordered, we would expect just to see nuclear relaxation or maybe some spin fluctuations, maybe a Gaussian. And in fact, what's seen are these rather strange low-frequency oscillations. And what are they? They can't be to do with magnetic order because we're too warm. So where have those oscillations come from? And they've come from this. So the muon, it turns out in this particular material, had fluorine in it, and the muon loves fluorine. And the reason the muon loves fluorine is because fluorine has a very, it's the most electronegative of all of the atoms, so F- is very, very attractive to muons. If there's F- in your compound, the muon will probably go for it. It will be the tastiest thing in your sample. And then what happens is that the muon will couple with the fluorine nuclei. And you get this rather interesting quantum coherence between the fluorine nuclei and the muon. So this shows you actually just for the coupling between one muon and one fluorine nucleus. You get these different energy levels, and therefore you get some transitions. These frequencies mix together and give you this characteristic response. So it's coming from a coherent interaction between the muon and very often two fluorine ions, and the muon has got itself between these two fluorine ions. You can calculate, this is the relaxation function that you would get in this particular case. It's a very simple quantum problem that you can work out. It's not that simple actually, but you can derive it. And again, this function is coded in to the analysis software packages that you will be using. Now, if you want a picture of what's going on, this is my animation of it. So here are two fluorine nuclei in a fluorine molecule, but in so you have to imagine, I haven't drawn it here, but there's a whole lot of other atoms in this compound. The muon goes in, it pulls the two fluorine nuclei a bit closer to itself, and now the muon is spin polarized. The two fluorine nuclei are not spin polarized, they're in some mixed state. And now what we're going to do is let time evolve. And as time evolves, in this animation I've calculated what the polarizations are on the muon and the fluorine, and I also let the camera pull back because I'm a frustrated film director. You know, that's what I would have done in another life. So what you can see is happening here is that the muon is spin polarizing the fluorine nuclei. They're acquiring spin polarization, and then they're causing the muon to see a magnetic field, and so the muon polarization is changing. So you can see the polarization of these species is changing as a function of time. So it's rather a complicated little dance that they do. As I said, you can calculate it. It's because the fluorine has this high nuclear moment, it's 100% abundant. The ionic radius is very small, the nuclear moment is quite big. So you particularly see this in in compounds containing fluorine. You can also see it in compounds containing protons and maybe some other things as well. It's very sensitive to these bond lengths, it's very sensitive to the bond angle. You can calculate it, and in fact it's an example of quantum mechanical entanglement. The muon is entangled with the fluorine nuclear spins. So you see it in PTFE, which is a fluorine-based polymer. You see it in these non-magnetic fluorides. So there are lots of examples of it. And this is an example of a magnetic material, cesium-2 silver fluorine. What you can see here at low temperature are the oscillations due to the magnetic order. And then at around 14 Kelvin, you go through the Nail transition. Now what takes over are these fluorine oscillations. And from which you can do things like you can measure the fluorine muon separation very, very accurately. So you know where the muon is sitting with respect to the fluorine. So time's running away with me a little bit, so I'll just skip over the next few examples. I think I'm going to just skip over those. You'll have those in the notes. But I just want to say again that all of these functions are available in WIMDA or the package that you'll be hearing about this afternoon from Roberto. Finally, the thing I just want to say, and you'll be hearing a little bit more about this, I think later in the week, is that something that I think is starting to become more and more important in working out which relaxation function to use is this thing that is called DFT plus mu. This is density functional theory plus mu, which is a method of numerically solving the lattice structures with a muon included to determine the muon site and to quantify perturbations. And although attempts to do this have been going on for a number of years, I think Roberto's group and my group in Oxford sort of reignited this a few years ago when we both had a very similar idea, which was to apply DFT techniques to look at fluorides. And the reason we did it for fluorides is because we know what the answer is. We know where the muon sits. And so now this has been extended to many other systems, organic systems, various other inorganic systems, looking at muon diffusion in copper, a whole range of things. A few example recent papers are shown here. And I think this has started to become a very important idea. It's also helped, I think, to make us think about what the distortions are that the muon causes. And this is a rather important thing I want to finish with. Recently, we looked at what we thought was a worst case scenario where the muon produces a distortion in a pyrochlore, and this has led to rather important ideas about the relaxation functions that we ended up seeing. So I just show you this little animation which shows you the muon going in to a pyrochlore lattice, and I've sped this up, the muon being turned on and off, just so that you can see the effects that the muon causes. It makes that bond go longer, it makes that bond rotate. You can see the positions of these magnetic ions are changing a little bit, and so the whole structure is being slightly distorted by the muon going in. By showing you a very rapid movement, your eye picks up where the large distortions are. So I think this is a very important direction that we need to go in to then help us decide what relaxation function, what local physics that we will be seeing. So I think my time is over, so I think after all those relaxation functions, it's time for some relaxation. I'll stop there. Thank you.